This conference will now be recorded.
Hello, I want to welcome all of you in our next webinar from the DigiFoF series. Today, we'll be covering case study using conceptual modeling for automatization of chemistry laboratory. Our presenter today will be Professor Juha Erning from University of Oulu. And before we dive into the topic of the session, I would like to tell you a few words about technical aspects. So, as in the past sessions, all the microphones are by default muted. So if you have any questions, do feel free to expand the GoToMeeting panel and use the questions or the chat functionality to let us know what we would like to dig deeper, where we would like to know a little bit more. Here you can see agenda of our webinar today, but this is something that I'll pass to our presenter. So without further ado, I'll give floor to Juha. So please accept the presenter and continue. Floor is yours.
Thank you very much, Mr. Chairman. So I'm Juha Röning, and as was introduced, coming from the University of Oulu. I am there leading a research unit, which I have named as a Biomimetics and Intelligent Systems Group. Today, with this talk, I would like to touch one topic area which we are covering, and it is robotics, and in this case, how we could use robotics to improve some of the applications where we need to do repetitive and time-consuming work. So in my talk, I would like to first introduce the topic itself, then concentrate a little bit how to collect the information. Then we make an initial model, how to refine the model, and what would be the next steps in this process. And then I would like to conclude my talk. And if you do have some questions, I'll try to do that, but follow Mr. Chairman's advice how to do the questioning. So in chemistry laboratory, there are quite many tasks which are very repetitive and relatively simple. In our case study, our aim is to use universal robot UR10 and some equipment which we can quite easily find from our laboratory to automate, or at least propose to automate, some repetitive tasks. We will create a model and refine it to the point where we can actually start implementing the code. We have also done some tentative implementations of the code, but during this talk, I will not cover that part because it would have taken a little bit longer time. But at least we will concentrate on conceptual modeling and how to do the refine step on that part. So as you know, the robotics has been stepping quite many steps outside the industrial environment. Earlier, it was very heavily classified that when a robotic arm was functioning, and if any humans were approaching the robot, it would stop it work. And that was for the safety reasons. So there were either optical fence or physical fence, so that anyone being inside the robot working area would cause that the robot will stop, and that way not harm anyone nearby. So in recent years, there has been a lot of research and development and already commercial products available where the robotic arm is designed that way that it can collaborate with a human being. Then the robotic arm is defined and designed that way that it will not harm a person. So it has only certain strength, speed, so that anyone being close it will not be harmed. And today we are just using as an example UR10, which is one of those arms available. So it has force sensors and some safety features so that the human can be easily nearby. It can be controlled over Ethernet, so it's readily available to automate and use whatever information you can grab from other sources. It has also a Python interface, so it's easily to harness and interface to your applications. Also, the luxury of it has a quite wide array of end effectors available, and it has control blocks by which you can attach different sensors, so it has configurable digital and analog I/O. In this case, we are using just a simple potentiometer with interchangeable electrodes to do the automation. This HAC HQ40D has a USB interface, so it can communicate and inform to the robot its measuring units, and especially if you are looking processes in chemistry, simple potentiometer to measure the voltage and the electricity conduct is enough. So we will look absorption experiments. Absorption is one of the most popular methods for removing pollutants from wastewater. So the absorption pollutants are adhered to the absorbent, and the aim is to try to find new absorbents for wastewater treatment, either for industrial or domestic wastewater. The aim is to test effects of different factors such as variation of temperature, pH, pollutant concentration, mass of absorbent, i.e. the bed volume, and ionic strength. Requires a large amount of experiments, and there is only a little bit difference between the experiments itself. Some of the experiments are monotonous and time consuming, and so it's just a very good target for the automation. The beauty of absorption method is that it's effective, it's economical, and it is cheap. Normally, if we are following the experimental chemistry experiments, we should be logged in the laboratory journal. The journal should be very detailed enough to duplicate the experiment. So we thought that that's a good starting point for deciding the automation. But if you look, and my apologies, this laboratory journal is in Finnish, but you can see that it is quite detailed information about the steps. So chemistry, a human being can easily follow these, but it is not so straightforward to make this as a robotic exercise. When we start, we can easily see it's sequential, and we can easily transform it to as a flow chart. So in this flowchart, we have just quick and crudely taken mostly the subtitles of the laboratory journal. But honestly, it doesn't help very much yet. So it needs some refinement process. So first, let's look what are the interesting parts. So first we have to find the parts and prepare the absorbent so that we select which one we like to take. And then we have some tests for the absorption. Preparing this absorbent is different for each tested absorbent, and we think that there is not very much point in automating the first part. I mean the box, which is now marked as a red square. What we are interested are the absorption experiments, and you can see that they are quite repetitive. If you follow stability test, optimizing the pH, effects of mass sorbent, effects of concentration pollutants, and so on. We will have a closer look on some of them. This level of detail is enough for laboratory technician or chemist to repeat the experiment, but honestly not enough for a robot to do it. So first, let's look the weighting. Honestly, weighting needs a special equipment or complex programming. For humans, it is relatively easy to do, and therefore we think that this is not good target for automation. I mean, for example, handling a spoon or estimating weight when mass is in milligrams. Then adding solutions. Handling the pipette with robotic arm is not quite as straightforward as you may think. Automatic pipettes are designed to be used thumbs, and volume adjustment is usually mechanical. Taking the pipette needs some more details that we can show in later transparencies. So we think that still this needs some refinement. There are some pipetting robots available, so we decided that we will not go deeper on this side. So then the following step is to do the adjusting pH. And here you can see with the flow chart that it's starting to get more complex, and there are actually more choices available. So, for example, adding some samples at sheet or a base, compare it to the previous pH adjustments. Then measurement. So we think that this is the level where we have enough details so that we can start implementing the code itself. So take the electrode from the track. So that would mean move the grabber to the electrode, grab the electrode, lift the electrode. Read value, start steering with electrode, send measurement command to the meter, wait the response, store the value, stop steering. Direct commands to our system and can easily be understood as a code which we can run and execute. Wash the electrode, wash the electrode, move electrode to the washing station, lower electrode to the washing water, gently steer electrode in the water, lift electrode from the water, shake excess water from electrode, move electrode to the drying station, sweep drying paper with the electrode. Again, quite straightforward, and we can imagine executive code following these lines. Then add LICL solution. So again, if you follow the lines, it is quite straightforward code as a result. So with this level, we can start creating the code, executive code. And then put electrode to the buffer solution. So now, depending what's the pH level, we either move electrode over the rack, lower electrode to the rack, release electrode, move electrode over the buffer solution, lower electrode to the buffer solution, and then continue from the same line. So this is the level we have developed our model, and we have already tentatively tried directly these measurement control flows and created algorithms and also operated it with a robot and with some sensoring elements which we have had. But there are still some things to be done. We need to finish some of the other refining models. We should look more carefully which parts should be automated and which part should be done by person, and then do the final implementation. So to conclude what I have covered today, we think that there is a very good potential for automation in research laboratories, and we didn't know, or I didn't realize that how topical this is when we think about the COVID-19 flu epidemic, what we are now realizing. We have done some proposals where we are trying to help some of the local laboratories to do the repetitive work, and hopefully also that way help a little bit in this serious situation. When using the models for designing these needs, we can find a correct level of detail. We need this detail level for designing the cyber physical systems. There are limitations, mechanical limitations, there are sensoring limitations, speed and other factors which needs to be carefully thought before the final implementation has been done. So thank you for your interest. I'm ready for the questions if you do have any.
First question that I have is at the very beginning, you have shown two example elements of equipment, so and the meter and the universal robot arm, did you also consider other items that could be used in this scenario?
Yes, we have in other applications and also I think in this application you can surely also use, for example, hyperspectra camera to see the difference and even do some analysis in an automatic way. We have also used some passive vision system and active vision system to control the movements and the location of robotic arm.
Thank you very much. And second question, after you have shown the journal of the experiments, you have shown it as a flowchart. Did you consider using, apart from flowcharts, from using UML, did you also consider using BPMN, business process model and notation process diagrams?
Yes, we have another application where we actually are doing it also and using it. So definitely that was also option for us, but this study was done using this kind of modeling.
Thank you very much. I'm looking at the chat, so if you have any more questions, this is a great moment to ask. Don't see any more questions coming, so I would like to thank you very much for your very, very interesting presentation. I did not think that it is possible to use robotics in such a scenario, so this has incredible potential for even the current situation. And as always, I would like to thank all of you for participating, for being with us today, and to invite you for the next webinar that will take place next month. Thanks a lot.
Thank you.
And have a great day. Bye-bye.
Bye-bye.
Bye. Thank you. Bye-bye.
Thank you. Bye-bye.